Welcome. Today I'm going to talk to you guys about interactions. Now, interactions are actually the force pairs that you might have heard about that go along with Newton's third law of motion. For every force, there's an equal but opposite reaction force. If you take the action force and the reaction force together, you look at them both, that's what we call an interaction. And so I've drawn out something here I want you to take a look at. Let's imagine for a moment that we have a cart that has a mass of 1 kilogram. Now, it's on a track, and on that track is also another cart, which happens to be stopped, that also happens to have a mass of 1 kilogram. If I give this this blue cart some velocity in that direction, they are going to collide. So that should make sense to you. Now, much of what we talk about this unit has to do with collisions, so I'm going to use that as an example. So in this case, the blue cart is rolling along until it comes into contact with the red cart. Now, when it hits the red cart, it's going to collide, right? And because this one is moving and this one is not, you can imagine that the blue cart is going to apply a force onto the red cart. And so you're going to see that the red cart here feels a force in that direction from the blue cart. Okay? So it has a force from the blue cart that is pushing it in that direction. Now, I think you'd agree, because of Newton's second law of motion, that anytime there's a force and a mass, that mass is going to resist the action of the force, and it's going to resist the acceleration that occurs as a result. And so that mass right there is going to be basically a resistance. And so this is going to change its motion, but it's going to have that mass that resists it. And so while this one is trying to push this one, this is going to resist. Now, what does that feel like? Well, I want you to think about this for a second. If you've ever played baseball or softball or volleyball and you've totally missed whatever you were swinging at, or for, like me, soccer, right? If the ball is rolling along and you go to wind up and kick it and you totally miss, that has never happened to me. I've never felt this, but people tell me this is what it feels like. If you ever feel that, where you expect to kick the ball, or you expect to hit the baseball or the softball, or you expect to spike the volleyball, if you expect to feel it and it's not there, it ends up causing some problems. It feels weird to you because you don't have that resistance resisting the force that you're trying to put on the object. And so when there is the ball there, it does resist the change in the motion that you're trying to affect. So what you see here is that the blue cart is trying to affect the motion of the red cart. It has to, because the blue cart is trying to go that way. And so the blue cart applies a force, but that force is resisted. Now, when you do kick the ball or hit the baseball or hit the softball or the volleyball, you can feel that resistance, right? You feel that somehow. And that feeling is the force that gets applied back on you. And so the same thing happens here. The blue cart, when it contacts the red cart, is going to apply a force in that direction. But what does the blue cart do? Doesn't the blue cart slow down as a result? Why does it slow down? It must be because of a force. And so that force that it feels must be because of the resistance that it experiences on the red cart. And so the red cart, we say, applies a force back on the blue cart, in this case, like so. And if I drew it just about correctly, that's pretty close. They should be exactly the same strength. So this resistance here causes the same force on this side, on the blue cart, that the blue cart is applying back on the red cart. And so we have this force over here, red, like so. That right there, this action force and this reaction force is what we call an interaction. And it's the basis for Newton's third law. Okay, so now we've got the idea. Now I'm going to tell you what Newton's third law says. Now, you may know that Newton's third law says for every force there's an equal but opposite reaction force. The nice thing about that way to say it is that it's very easy to memorize. You probably already have it memorized, right? So that's how easy it is. In reality, though, it's missing a couple of key details that I think lead to some problems later on. So here's how I would say it. and it is a little bit more complicated, so just bear with me. For every force, in this case that's the action force, applied by object A on object B, okay, so you have an object A and an object B, and A is pushing B, there results a reaction force applied by object B back on object A. And so as the A object is pushing on B, we find that B is resisting and pushing back on A. So I've drawn three situations up here that have to do with Newton's third law of motion. I could have drawn hundreds, millions of these up here, but I took three that I think are pretty representative of things that you're going to see in the class, things that you might have to do in the class, for example. So we're going to start off with just a guy jumping. So this is a guy jumping here. He is hopefully got a bigger vertical leap than I do. And so he's got his knees bent, and he's let his weight sink down just a little bit, and then he's going to flex his legs. And when he flexes his legs, he takes the floor below it and applies a force downward. So that force is being applied downward. Now, I think you'll agree that the force on the floor is applied and resisted by a huge amount of mass. So that mass on the floor, absolutely huge. It has a huge resistance to that force. So most often when you try to jump, you don't break through the floor. So the resistance and the structural integrity of the floor support your weight and the additional force that you're trying to apply. So we say it has a huge resistance. And so that force that you apply downward is resisted by the mass, and it causes a force to be applied back upward on you. So here's you, right? If you're the guy, right? And so you feel a reaction force back upwards as a result. So you pushed on the floor, and the floor pushed back up on you. And that's why you jump up into the air. If you're not me, I don't have any vertical leap. So it's sad, but it's true. What about rockets? How do rockets move in space where there's nothing to push against? Well, the answer to that is that they bring the stuff that they push against with them when they go up there. So they have a fuel inside, and that fuel gets heated up and it expands, and then it gets pushed out the back. And so if I look at this here, the rocket is applying a force to the gases that are being pushed out the back. So those gases, even as low mass as they are, they resist a change in their motion. And so when the rocket pushes them back out the back end, they apply a force back on the rocket because of that resistance. And so the rocket feels the same force, just in the opposite direction. And that's, of course, the reaction in that pair. So here's the action force, and here's the reaction force. And it's really the reaction force that gets the rocket to move, just like it was the reaction force that got you to come up off the ground when you jumped. Last but not least, what about your car? I think you'd agree that the car, the engine in the car just spins the wheels, right? So it spins the wheels. We're going to talk about rotary motion later on. But for right now, let's just talk about what happens where the wheel meets the road, right? So the wheel tries to spin because the engine is trying to spin it. And so it applies a force backwards on the road. So the wheel applies a force on the road. Now, if there's enough friction, which in Wisconsin is a question, right? If there's enough friction, the force that the car actually feels is due to the resistance of the road to the force that the car tires are applying. So if the tires are applying a force backward on the road is applying a force forward on the wheel. And so the wheel itself feels a push forward due to the reaction force. And so you can see why you'd want to try to think about these things together, right? You want to try to use a complete interaction description because it's going to help to explain why things happen, why the forces are what they are. So there's a simple way to look at this, and that is to think about it in terms of a simple sentence. And the sentence gets a switch in it, and you can always use this to try to figure out where the action and reaction forces are. This is what I think of. So the action force is usually easy. It's the thing that is choosing or is forced to apply a force to the other object. So in my case, for jumping, it is me pushing down on the floor. That's if I wasn't here to do that, then there would not be that force on the floor. So that is the action force, right? So I'm going to say, I'm just going to use some letters here. So I'm going to use A right here. So A applies a force on some other object, right? So let's say that object is B right here. So A applies a force on B. Two different objects. A is applying a force onto B. So the reaction force then is just switching them, okay? So it's that simple. Switch them around. Boom. Pull a big switcheroo on them. No big deal. There we go. There it is. So if A applies a force on B, then B applies a force on A. That's as simple as it is. It's not any more complicated than that. Now, where it gets weird is with things like gravity. So gravity applies a force on objects, and we've talked about that a little bit, but I want you to think about this in terms of Newton's third law. So the Earth applies a force on me right now. That's why I'm sticking to the surface of the Earth. So the Earth applies a force on me, but Newton's third law says if the Earth applies a force on me, I apply a force on the Earth. So believe it or not, right now, I weigh 800 newtons. That's how much I'm being pulled down by the Earth. The Earth is experiencing an upward pull from my gravitational field of 800 newtons. That's what Newton's third law says, and it's actually true. I apply a force on the Earth just like the Earth applies a force back on me. Now, why don't we see the Earth flying all over the place? Obviously, the Earth has a lot more mass than I do. My mass is about, I don't know, so let's say 50 kilograms. The Earth's mass is something like 10 to the 24th kilograms. So 1 followed by 24 zeros. That's a lot of mass. So for me to apply my tiny little force onto that much mass, there's a huge resistance. And if you think about how much acceleration that would be caused by that, it would be completely non-measurable. And so that's why you don't really see any reactions as a result.